Hello, welcome to our lesson today on the method of three-moment equation, using it to analyze statically indeterminate structure. My name is Engineer Dr. Edidiong E. Ambrose from the Department of Civil Engineering, Kwai State University. So we will be looking at the following content: introduction, derivation of three-moment equation, and we look at beams with simply supported end, we look at beam with fixed end, and then we look at beam with cantilever end. So when we talk about three-moment equation, it is a simplified method of structural analysis that is used to analyze continuous beams and some other statically indeterminate structure. It was derived by Emile Clapeyron in 1856, and it basically uses differential equations of beam bending. And so he derived this equation, that the equation relates moment at three consecutive support to applied load of an adjacent beam. Usually you have three consecutive support, that is two spans. The equation relates their internal moment with the successive applied loading. And the theorem states that if a beam has n supports, the n ones being fixed, then the same number of equations required to determine the support moments may be obtained from the consecutive pairs of spans. That means if you have span A, B, B, C, span B, C, C, D, they can work together. That is two spans, two consecutive spans can be working together. And so in doing that, you will be able to derive a set of simultaneous equations in which when that simultaneous equations are solved, the support moment will be determined. So let's start with this diagram. If you have, this is a continuous beam of two spans, span AB and BC. So there are three supports and two spans. The support are support A, support B, and support C. And the beam is carrying a uniformly distributed load of W per length. Now this is the elastic curve of each of the span. That is the deflected curve. In life, real life is not always obvious like this, but we exaggerate it for the sake of explanation. So this is the elastic curve for support span AB, and this is the same thing for span BC. So if you stand at support B and draw a tangent to the elastic curve, like this tangent A prime B, so you draw a tangent, that tangent makes an angle theta B at this. If you do the same thing at this span BC, it makes an angle theta BC at this particular point. Now, this is the length of the first span L1, this is the length of the second span L2. So if you come down here, you see what we call M over EI diagram. That is moment divided by the flexural rigidity. This is for the applied load. Applied load is a UDL, and for a UDL, this is the shape of the simply supported bending moment diagram for this. So that is the shape, and this is it for this other one. And if you look at this is a centroid. So the centroid, this is a centroid, and the distance between the centroid of that moment diagram to the external support is x1. For this one is x2. And so this is another M over EI diagram for moment at support B. When support moment at B, it will be up minus this. So if you, this is how it varies to this support. It varies to this end support. Is maximum here and 0. So that's how we draw this diagram, and it gives us this triangle, which if you split the triangle, the left hand side is the centroid for the triangle at the left hand side, and it's a triangle. Since it's a triangle, the distance from the centroid to the external will now be 2 over 3 L1. The same here, 2 over 3 L1. Now for the end moment that support A, this MA. So it is maximum here, and it varies to support B at 2 is 0. The same thing happens here at MC. So if you take the centroid, the real distance, this is the centroid of the triangle, and the distance from this centroid to the external support is what? 1 over 3 L1. That's from simple geometry. This one is 1 over 3 L2. And so if we, or this is where the parameters are defined. Now E1, I1 is a flexural rigidity for span 1 and this flexural rigidity for span 2. Now if we assume, let's look at support B. If we assume that this support is continuous, what it means is that theta BA and theta BC are the same in magnitude but opposite in direction. So if we assume that, it means that theta BA plus theta BC equals to 0 because they are the same in magnitude but opposite in direction. And let's call that equation 1. Now, if we use the concept of second moment area theorem, so this is what we have. Even if we don't use that concept, if we say this line tangent proceed to this place, and so if we say the distance from this tangent, where the tangent up to where the A was, that is A prime, this forms a triangle. A prime B, that is a triangle. And from simple trigonometry, you can say that tan BA is equal to A prime all over L1, that is tan theta is equal to opposite over adjacent. So that is why we come here, we can say that this theta BC is equal to A prime over L1. This is supposed to be tan BA, but you know, for very small angles, tan theta is the same thing as theta. So that's why we say theta BA equals to A prime over L1. So let's call this equation 2. So now, from second moment area theorem, we know that A prime can be defined as this centroidal distance multiplied by the area of the M over EI diagram between A and P. That is between this point and this point. We can find the centroidal distance and multiply by the area of this E over I, M over EI diagram. But now we must note that the actual M over EI moment is a summation of the one due to applied load AB, and the M over EI diagram due to support at A and B. So we are going to do it bit by bit. So that is what we are going to do. Each of them we are going to multiply the subtract the distance between the central, that's the central distance, by the area of the M over EI diagram. So if we go to the first one, which is the applied load, so the area of that we are looking at between span point A and B now. So the area of this M over EI diagram for the applied load is A1. The central distance one is X1. That is what we have here, A1 and X1. Meanwhile, we have factorized EI out. So that's why we have factorized E1, I1 out. That's why we have 1 over E1, I1. So that we don't need to multiply all of this by E1, I1 again. So this is for the applied load. If we go back for the next one, this is for MB. For MB, the area of this is a triangle. So the area is going to be half base times height. So what is the base? The base is L1. What is the height? The height is what? MB. What is the central distance? The central distance is 2 over 3 L1. So that gives us this component. Now the area, this is the area, which is half base times height. This is the L1 is the base. There MA is the height, and all of them divided by 2. This is the central distance, L over, okay, sorry, we are doing for M1. Let's go back there. I think he started with M1. The M1 is a triangle half base times height. The central distance for MA, sorry, is 1 over 3 L1. So we can go back there and say this is the MA is a height, L1 is the base, all of them divided by 2. The central distance is L1 over 3. Now for M2, MB, the triangle is half base times height, which is half, the base is L1, the height is MB. The centralized distance is 2 over 3 L1. So we can just go here and say this is half of base times height, and this is 2 over 3 L1. If we simplify this, this is what we will have. So we can call this equation 3. Now, if you put equation 3 into equation 2, what was equation 2? Equation 2 was theta b. A is A prime all over L1. So that what it means is that we have, this is A prime. So we just divide it by L1. So if we divide it by L1, remember we had factorized A1, I1. So we'll also put 1 over L1. And the rest will still be the same. If we simplify it, this is what we will have. Let's call it equation 4. Now, similarly, if we do the whole process again for span BC, we will have something like this. So this is equivalent of this bit for span BC. Let's call that equation 5. And then we go ahead and put equation 4 and equation 5 into equation 1. What was equation 1? Equation 1 is that theta BA plus theta BC equals to 0. So if we go there and say this is theta BA plus theta BC, we equate it to 0. That gives us equation 6. If we process, simplify it, this is what we will have. If we process this, this is what we've simplified, this is what we have. Now, to multiply through by 6, we multiply through by 6 to cancel all the 6. So this is what this gives us this, which is equation 7. Now, equation 7 is a 3-moment equation that relates the 3 support moments with the applied loading of 2 adjacent spans, that is AB and BC. So that is what we use. Now, if EI is constant, that means E1, I1 is the same thing as E2, I2. Then we can cancel them out and the equation will be reduced to this equation 8. So just note the pattern. This ML1 plus the middle span 2MB into L1 plus L2 plus the last support MCL2 is equal to 6A1 X1 all over L1. All these parameters we know. These are the area and the central distance. So equation 8 is what we can use to solve any continuous beam using the method of 3-moment equation, which is what we are going to do from the next slide. So let's solve this example 1 to demonstrate the application of the 3-moment equation. Example 1 is analyze a continuous beam beside and draw the bending moment and shear force diagram indicating maximum moment and shear forces, assuming that EI is constant in both spans. So you have 2 spans here, span AB and span BC. It's a concentrated load here, it's a uniformly distributed load. So this is how the solution is. Now the simply supported bending moment diagram of span AB and BC is given like this. So this is a simply supported bending moment diagram. When we say simply supported bending moment, is taking each span as if they were simply supported and drawing the bending moment diagram for each of them. So this is for span AB. We have a concentrated load at midspan, so we will have a triangle that peak at midspan, and this point is PL1 over 4. That is a standard formula. You might need to memorize this. PL1 over 4. By the time we do PL1 over 4, it gives us 90 kilonewton meter. So that is a peak. While this one will be an arc, a semicircle form kind of, and the peak here will be WL1 squared. Okay, this is actually L2, not L1. This place is L2, please take note. So WL2 squared over 8, and that when we did it give us 45 kilonewton meter. So now what is the central distance? So this is an isosceles triangle. So the central will be at the middle, such that this distance, central distance from the central to the external support will be half of L1. L1, remember, is 3. So this middle is what? 1.5. And the same thing, this span L2 is 3. So the middle one, the central distance here is 1.5. So the next thing is for us to calculate that parameter. to calculate A1, that is the area of this moment diagram. And the area is, which is a triangle, so the area is half base times height. So that's why we have half. The base is 3, the height is 90, so that gives us this value 135 kilonewton meter. Now for A2, the area of this semicircle is 2 over 3 BH, where B is actually 3 meter, this base, and H is the height of this, which is 45. So that's why we have 2 over 3 times 45 times 3. That gives us 90 kilonewton meter. Then already we know that central distance for x1 and x2 is 1.5, and the length L1 and L2, they are both 3 meters. So the next is to apply the 3 moment equation. We write this is the 3 moment equation for this to span. So by the time we come here, we put the parameter. L1 is 3, so L1 MA is 3 MA. Now to this other place, L1 plus L2 is 3 plus 3 equals to 6 multiplied by this 2 equals to 12. So that's how we have 12 MB here. And for this place is MCL2. L2 is 3, so that's why we have 3 here. So this is 6 times A1 times X1 all over L1 minus 6 times A2 times X2 all over L2. So by the time you work out the whole of this, it gives us minus 675. So we can now say that 12 MB. Now take note that because this beam is simply supported, so moment at A is 0 and moment at C is also 0. So that's why we say that for simply supported in MA and MC is 0. So that simplifies this equation to 12 MB equals to minus 675, in which if you find MB by dividing this by 12, you have minus 56.25. So what it means is that the moment at support B is that minus 56.25 kilonewton. So the next thing is to calculate the support reaction, and I'm going to use a different method of calculating support reaction other than what we use in moment distribution and slope deflection. So we are drawing back the beam. This is the beam that we had. This is the beam that we had. From this beam, this is span AB and this is BC. These are the external load. So what we have come is to introduce this load moment MB is a minus, so it's an anti-clockwise moment. So we have an anti-clockwise moment here of what? 56.25 kilonewton meter. So what in this method we use the basic definition of moment distribution of bending moment. Bending moment says, what is bending moment? Bending moment is the algebraic sum of the moments of all the forces either to the left or to the right of a section. So that means if we know the bending moment at the section, we can stand at that section and take the algebraic sum of moment of all the forces either to the left or to the right and equate it to the bending moment that we know. So this is what we are going to do. First of all, we are going to stand at B. So if we stand at point B to take bending moment, so let's take it to the left hand side, because by the left hand side we have one unknown VA that we want to find. So we are standing at B, walking at the left hand side. So if you are taking, remember the sign convention is that clockwise moment are positive, anti-clockwise moment are negative. So if we stand here to the left, the first moment, the first force is VA. So moment due to force VA will give a clockwise moment. So it's going to be positive. So the moment due to VA will be VA multiplied by the perpendicular distance between A and B, which is 3. So that's why we have here 3 VA. The next force is this 120 kilonewton force, and it's going to produce an anti-clockwise moment. So that's why it is negative. So what is the moment? Moment is this force multiplied by perpendicular distance. The perpendicular distance is 1.5. So that's why we have minus 120 times 1.5. And then we equate it to the moment, bending moment that we know here. which is what? Minus 56.25. So we now have this equation with only one unknown. So if we solve for unknown VA, it gives us 41.25. So we know the value of VA now. We can now go and stand and take moment to the right hand side just to find this unknown VC. So this is what we do. But you need to take note that when we are doing it to the right hand side, the sign convention will change. The sign convention will change such that clockwise movement becomes negative, anti-clockwise movement becomes positive. Please take note of that. If not, you will make a mistake. So we now stand here. The first force is VC, a reaction at C, and is going to produce an anti-clockwise movement. And in this our new convention, anti-clockwise movement is positive. So now the force VC, the perpendicular distance is 3, so we have 3 VC. The next moment, the next force is this UDL 40. The UDL is going to produce a clockwise movement. But in this our new sign convention, clockwise movement is negative, so that's why we have negative. The UDL is, first of all, we convert it to a point load, which will be 40 multiplied by the distance. That's why we have 40 times 3. The UDL will be, when we change it to point load, the point load will be located halfway of the UDL. That makes the perpendicular distance 3 over 2, which is 1.5. So that's why we have multiplied by 1.5. Then we equate it to the moment that we know, bending moment MB, which is minus 56.25. So if we solve for the unknown VC, that gives us the reaction at C as 41.25. For us to find MP, the best thing is to do is to use sum of vertical forces. That is sum of vertical force equal to 0. So add all the vertical forces, which is VB plus, that means if you just find VB, that will be VB minus 120 plus, sorry, that will be VA, which we know to be 41.25 minus 120 plus VB minus 40 times 3, then plus VC. If we make VB the subject of the formula, this is what we will have. We will have that VB equals to this, in which if we solve, it gives us this 157.5. So we now know our support reaction. That means we can easily draw our shear force diagram and our moment, bending moment diagram. There is a note here about maximum span moment. The maximum span moment in span AB will be at mid-span. That is because span AB has a point load. The maximum moment will be at under the point load, which is at the mid-span. But for span BC, it will not be the same. The span BC being that by the time you draw the support moment diagram, which is just moment support B is 56.25, so you just draw this to 0. At support A is 0, at support C is 0, so this is what you have. So you can now, when you want to put to draw the bending moment diagram for span BC, this is what we will do. You know that if you come back here to that this diagram, remember this place, the simply supported moment is what? 90. And what we do is to superimpose the simply supported moment on the support moment diagram. So the simply supported moment is a triangle that peaks at what? 90. This peak is PL over 4 because the load is at mid-span. So if we bring that to superimpose here, in this case it is inverted. So we will have at the mid-span here, the moment at this point should be what? 90. But that 90 is not starting from origin. 90 is starting from here. So how do we know the value at this point? This beam is moving linearly from 0 to 56. So the value at this point will be 0 plus 56 divided by 2. That will give us the value of this point. So when we know the distance from here to the origin, we subtract it from the 90, and that gives us this. But we cannot do the same thing here. because this one is not at mid-span and we don't know exactly where the maximum span moment is, because this is 56 and this is 0, and we cannot just bring this and put and know the middle. So what we do for us to know what is the maximum span moment and where does the span moment occur, we need to use the basic concept of bending moment and shear force. The relationship between bending moment and shear force says that at the point of bending moment, the shear force equals to 0. Notice. So what do? We have to go back to write the equation. So we go back here to write moment equation for span BC. For the span BC, we write moment equation. That is basic strength of material. So how do? We just, there is a section, it is the moment equation for span BC. In case you don't know, you need to go back to your basic strength of material. So we write this moment equation for span BC, and then we write the shear force equation. The shear force equation will just be by differentiating moment equation. So if we differentiate, this is a shear force equation for this. And now we know that at the point of maximum bending moment, shear force equals to 0. That is why we go to this shear force equation and equate it to 0. We just equate this equation to 0. And when we equate, remember we have an unknown x. We solve for that x gives us 4.75. It means that maximum bending moment will occur at a distance 4.75 from here, from this origin, which should be somewhere within this one, because from here to here is 3. So for us to know what is the value of the maximum moment, we take this x equals to 4.75, we come to this bending moment equation and substitute 4.75 or 4.97 for x. So anywhere we see x, we put 4.97 and calculate. This is what we did here. And the maximum bending moment gives us 21.27. So that was how we know that the maximum bending moment is here, which is 4.97 from this distance. If you want to do from here, it will be from here to here. Here is 6, so 6 minus 4.97 give us 1.03. That means the distance from this right support to where we have maximum bending moment is what? 1.03. The maximum bending moment is what? 21.27. So by doing that, we have drawn our bending moment diagram. Our shear force diagram, as usual, as of course, we should know how to draw, but just in case you don't know, we start at the origin. Remember, this is the diagram. We start at the origin. There is a reaction here, VA, going up, which is 41.25. So we push it 41.25 up. But between this distance and this point load, there is no load. So this will vary, the shear force will vary vertically, or sorry, horizontally. But when it gets to this point, there is a force of 120 kilonewtons. So that force will push it down by 120. You know the distance from here to here is already 41.25. So what remains from 120 after 41.25 is 78.95. And between this distance and here, there is no load. So it will move again horizontally here. When it gets here, there is an upward reaction of 157.5. So it will push it by that amount. But remember, from here to the origin is already 78.75. So what is remaining when you subtract that from 157.2 is what? 78.75 here. And then this is a UDL. A UDL always vary shear force linearly. So this will vary linearly be across this distance, but the magnitude will be 40 times 3, which is 120. So you will go 120. From here to here is 78.75. If you subtract it from 120, what is remaining is 41.25. And this support reaction at C will push it up by what? 41.25. That will take it back to 0. And by doing that, when you start at 0 and it ends you at 0, it's always a sign that your calculations are right. So this is how the first example have been solved using the moment of 3 moment equation. The next thing is for us to look at the second example. And so the second example, you can watch out for part 2 of this video to continue from where we stop. Thank you.